All right, good morning. Okay, so we'll start. So before we continue on machine learning and neural networks, so you may have seen that the grades for Project 1 have been released on Gradescope. If you have questions about why you have obtained the grade that you have obtained, please feel free to send us an email and we'll reevaluate if necessary what you have submitted. You should also be aware that the second project is also released. So you have all the instructions as usual on GitHub, and you can start working. Everything that you need for the project has already been covered in class. So you can go ahead and start working on that project. Okay? Do you have questions about this? No? Okay. All right. Then today we'll continue talking about machine learning. So just to do a quick recap of what we have covered last week. So the main thing was that we were trying to solve this very generic problem, which we call supervised learning. So this is the case when you are given a data set of pairs of inputs and outputs, and you want to basically identify a function or a conditional probability distribution that would map the input to the output. Okay, so you start from some, for example, X vector or X image, and you want to produce some Y output. Okay, and we frame that as in terms of a probabilistic model. So for us, when we say that we want to solve this supervised learning problem, it will mean that we'll first postulate a probabilistic model, so a conditional distribution for the output given the input. Okay? This probabilistic model will come with parameters, and then we'll try to identify these good parameters given the input-output examples that we have in a training set. Okay? So we saw two main algorithms so far, or two main models so far. The first one is linear regression. So this is when the output is just a real value, and you start from a vector of inputs, and you want to go from this vector to this real valued output. And in this case, in the case of linear regression, you assume a linear relationship going from the input to the output. Okay? And so we did that in the context, again, of a probabilistic model, where we said that, okay, in linear regression, we assume that the conditional probability distribution of y given x follows a Gaussian distribution, where the mean is a linear combination of the inputs, so W transpose times x plus some offset, and the variance of this Gaussian is fixed or something to be learned from the data. Okay? Then once we have a probabilistic model and we have a data set, to identify the parameters of this model, we just follow the principle of maximum likelihood estimation. Okay? So you maximize the likelihood of your data set, and then when you state this, everything eventually reduces to, in the case of a linear Gaussian model, to an objective function, which is the same as just minimizing the sum of squared error, and then you solve this to identify the two parameters, in this case, the W vector and the offset. Okay? Then we continued. We covered a second model, logistic regression. So this is something useful when you have not a regression problem, but a classification problem. So the output is a category, 0 or 1, true or false, positive, negative, cats or dog, and you want to produce this kind of prediction with a machine learning model. So again, we started from a probabilistic model. In this case, we defined a conditional probability distribution of the positive class py equals to 1 given the input x. As following this model, so this sigma of W transpose times x plus b, where sigma is what I call an activation function, in this case, the sigmoid activation function defined as 1 over 1 plus the exponential of its input, and which looks like this in the figure. Okay? So this model, or this output, gives you not a value which is true or false, 0 or 1, but gives you a probability of the positive class. So it gives you a number between 0 and 1, which you can associate to the probability of the positive class. Okay? Then, given this probabilistic model, again, we follow the principle of maximum likelihood estimation to identify the parameters. We unroll this objective, and we arrive, in this case, to the minimization of the cross-entropy loss over the training set. Okay? Unfortunately for this one, we don't have any analytical solution, contrary, for example, to the case of linear regression, where we can solve this problem directly on paper. For the logistic regression model, we can't. So we need to do something else to identify the parameters. And in this case, the trick was to use a numerical optimization algorithm to approximate the solution. Okay? And in the case of what we'll cover in this course, we consider the algorithm of gradient descent, which starts from some approximation of the parameters and then tries to improve it by just following the steepest descent, or the direction of the steepest descent to update the parameters. And you repeat that over and over until you don't see any improvement on the loss that you are trying to minimize. Okay? All right. Okay, so now what we'll see today, we'll talk about neural networks, and we'll see how to build them or to compose them from the two previous models that we have seen, so linear regression and the logistic regression model. We'll see that we can actually compose these two models together to obtain what we call first shallow neural networks and then deep neural networks. Okay? So I will define a shallow neural network as a probabilistic model taking as input a vector. Okay, so we have x, which is a vector of some dimension. Here in the slides, I use d in to denote the dimension of the input. So we have vectors, for example, of, say, 5 elements as input. And in a shallow network, these vectors are mapped to an output by going through an intermediate representation, which we call a hidden layer. Okay? So we'll have the output, which can also be multidimensional. And we'll go from x to y by going to an intermediate representation, which we call a hidden layer. Okay? And this hidden layer will be a vector of size, what's the q? Okay? And so the kind of diagram I will usually draw is something like this. And each element, in particular of this vector, this hidden vector, is computed from all the input of all the elements in X. Okay? So this will be Hj, and I will define Hj as a logistic regression unit, actually. So it's the result of the activation of some activation function applied to a linear combination of the inputs, so of the X elements. Okay. So that means to compute this value, okay, we just need to iterate over the element in the input vectors. Okay, and then for each of them, we multiply by some coefficient WGI, okay, where these WGI are specific to this unit J. You compute all these products, you sum them, and then you also add some offset Bj, which is also specific to this unit Hj. Okay? So effectively, that means this vector, sorry, like this, H will be composed of a first hidden unit, H0, then a second, and so on, up to Q minus 1. Okay? And then, once we have computed this hidden layer, this hidden representation, how do we compute the output, or each element of the output vector? Well, we'll do something similar. So if I take, for example, this one, it will be computed by taking the values from the previous layer, so in this case, the hidden layer H. You multiply them by some coefficient. Okay, you sum, and then you add some offset. Okay, so we'll have, so here you would have yk, where yk is equal to, so you iterate over the elements hj in the hidden layer, you multiply them by some coefficient, which are again specific to the output k, and then you add some offset, which is also specific to k. Okay? So in this case, this would go from j equals to 0 to q minus 1. Okay? Yes?
Why not take the activation function on the output?
Okay, I will come to that. That will depend on the kind of output values we want to produce. If we want to, for example, solve a regression problem where the output should be a real value, that can take any value on the real line. If you were adding an activation function, you would basically limit the support of the possible values that you can produce. Okay? But let's consider for now the case of regression where what we want to produce is really a vector of the outputs on the real line. Okay? All right. Okay, so I will start easy, and I will start by considering a very simple neural network with one hidden layer, with one input. So we have just a single element in X. Then we map this to 3 hidden units, and then we produce a single output. Okay, 0, 1. Okay, so mathematically it means that this output will be computed like this. So we compute each element in the hidden layer. So we have sigma some activation function times W0 x plus V0 plus sigma W1 x plus V1 plus sigma W2 x plus V2. Okay, so that these 3 values correspond to these 3 elements, and then to produce the output, we have to iterate over the element of this hidden vector, okay, and we multiply them by some coefficient, in this case V0, V1, V2, and then we add some final offset, which I will call C. Okay? The activation function I will use today is not the sigmoid activation function, but it's the ReLU activation function. So where I define sigma as value, which is the maximum between the input and the output. Okay? So effectively, you have something like this. So this is the input, this is value. You have 0. And so for any value which is negative, you return 0. And for any value which is positive, you return the value itself. Okay? Questions on this so far? Okay. Okay, so in the slides you have the same more or less diagram representation where, okay, here I'm using circles and on the blackboard I'm using these rectangles, but they mean the same thing. Okay, so we have the input, we have the output, we have the three hidden, we have the hidden layer and its three values, h0, h1, h2. You also see that each arrow is annotated with a coefficient. These are the coefficients that you see there or there. Okay. And implicitly, this circle means that we compute this weighted sum of the inputs, okay, to produce the output. And also, you see this green line here, which corresponds to the activation function, and it should remind you of the ReLU. Okay. You also see these two extra nodes. One, okay, which is another way to view the problem. Instead of having this offset, which we add explicitly before the activation function, it would be the same to just pretend that the x vector or the h vector comes with an extra element, which is constant, with a value of 1. Okay? And then we just multiply this element by some coefficients, which will be the same as these offsets. Okay? And so usually will not be as exhaustive as this kind of diagram, but I will summarize usually a neural network in this way or in this way. Okay? But you should realize that when I draw this, there is a lot going on in how all these values are being computed. Okay? Okay, so now visually, what's going on? So let's dissect this neural network element by element. So let's first look at these values. So you see in the first row possible combinations or possible values for the inputs before the activation function. So if we consider W0 times x plus B0, it defines a line if x is one-dimensional, okay, which could look like this orange line that you see at the top on the left figure. Okay? W0 will define a slope, and 0 will define some offset for the line. So the line that you see, of course, will depend on the value of this coefficient and of this offset. Okay? Now, for W1 times x plus B1, that will also define a line, okay, which could be also an increasing line, like you see in the middle. And for this value, we could have maybe W2 times x plus B2 being a decreasing function, depending, in this case, of the value of the coefficient. Okay? If the slope is negative, you will have a decreasing. Okay? So we compute this, and you see it here for the values of x going from 0 to 2. Okay? Then we compute the h value by just taking this input, passing them through the activation function, in this case the value. And so basically what will happen now is that the lines that you have will be truncated. You will just, everything which is positive will pass through the activation function, and everything which is negative will be set to 0. Okay? And this is what you see here, for example. We have the positive part of the function which passed through the activation function, so it's preserved. On the other hand, the part here on the left is set to 0, okay, because that corresponds to negative values of the input. Okay? And the same for this unit, H1, and for this one, H2. Okay? Now, we have computed these three values, H0, H1, H2, for values of x going from 0 to 2. Then these three values, these three functions are being rescaled, okay? And the rescaling happens here when we multiply them with V0, V1, and V2, okay? And so the effect of this product, you will either make, that will basically stretch the lines, okay? So it will make either the line steeper or closer to 0, but you could also flip completely the function if this coefficient is negative. Okay? So this is what you see here, for example. We have certainly a V0 which is negative and larger than 1. Because it's negative, it's flipped, and because it's larger than 1, the amplitude is larger. The same for the case in the middle. Not exactly the same. Here you have a coefficient V1 which is positive, so you don't have any flip, but it's larger than 1, and you see that by the steep of the line, which is greater than 4. And finally, here, for V2 times H, it's a positive coefficient, but smaller than 1, and you see that with the slope, which is smaller than before. Okay? So now we have basically rescaled or flipped our activation values. And then the final step is to sum them together and to add some offset. Okay? And this is what you see. When you add the three boxes, these three functions together, we obtain, for example, this function. What is interesting is that you should realize that by just combining these ReLU activation functions, we obtain a function which at the end of the day is piecewise linear. Okay, you see that it's made of linear segments. Okay, and maybe that's not yet clear for you, but the number of segments, the number of linear regions that you see, so in this case we see 1, 2, 3, and 4 linear regions, is actually directly proportional to the number of units that we have in the shallow network. Okay? And more precisely, what we have is that the number of joints here is proportional to the number of units. Questions on this? So that means it's very simple neural networks made of one hidden layer with 3 units inside actually defines a whole family of possible piecewise linear functions made of up to 4 linear regions. And the kind of functions you will obtain the functions that you will obtain will of course depend on the value of the parameters of this neural network. So in this case we have, what are the parameters? We have all the W coefficients, all the B offsets, all the V coefficients, and the final offsets. Okay, so we have 10 parameters, and depending on the values that we set for these 10 parameters, we will obtain one or the other piecewise linear function that you see there on the slide. Why is it? So do you think this is a powerful representation? Do you think we'll be able to, with this very simple model, to approximate any function that we want? So I see a few of you nodding. Why? Yeah.
If you have enough segments, you can represent an almost continuous function, which is one log.
Yeah, exactly. So the trick is to realize that you may have a very complicated function, but as long as you put sufficiently many hidden units in this hidden layer, so as long as the size of this as long as the size of this hidden layer is large enough, you will have basically a way to discretize your very complicated functions into small segments, and inside of which you will just fit a linear segment. Okay? And this may seem like trivial, but this is actually very powerful because that means you can approximate any functions to arbitrary precision. If you say that you want to have some approximation error up to, I don't know, 10%, you can just set sufficiently many hidden units until you reach this 10% error. Okay? And so this is something which has been formalized for a long time, which we call the universal approximation theorem of shallow networks. And it basically says that, okay, the number of Q of hidden units, Hj, you can basically interpret that as a measure of the capacity of the shallow network. So if you have few hidden units Hj, you have a small capacity, so that means you will not be able to represent very complicated functions. On the other hand, if Q is large, you have many hidden units, then you will have more capacity, okay? You will be able to fit more functions. And in the specific case of Rayleigh activation functions, the hidden units will define up to Q joints in the input space, okay? Hence defining Q plus 1 linear regions in the output space. Okay? Where what I call a joint is just these knees that you see between two segments. Okay? And then finally, in this setting, the universal approximation theorem states that a single hidden layer neural network with a finite number of hidden units can approximate any continuous function on a compact subset RD to arbitrary accuracy. Okay? So, if you have let's say some function, I don't know, like this would be f of x. You can approximate this function with a shallow network by just basically discretizing this or dividing this function into segments. So I don't know, you could have maybe so we would have, for example, this approximation. Okay, and you will argue that this is not a very good approximation of f of x. Okay, and I would agree with you. However, you can make this approximation arbitrarily accurate by just considering more and more and more hidden units. Okay, so for example, if you have twice as many units, you would have twice as many segments. Okay, and now we would have this approximation. Okay, which is already better. And if you want an even better approximation, well, you can keep increasing the number of hidden units. Let's say again by a factor of 2. We'll have something like this. Okay, and now you have an approximation which is quite close to the functions that you wanted to approximate. And so try to find a counterexample, you will not find any. Okay, you can prove really that there always exists a neural network that will be able to approximate arbitrarily well any function that you give it, okay, to arbitrary precision. And actually, this is a theoretical result that we have known since the 80s. Okay, and this is why it has been so frustrating for the research community, because this theorem proves the existence of this neural network, of this arbitrarily good neural network. But the theorem does not say how we should find them. It just says that they exist. And so this result is from the end of the 80s, but it's only since, I don't know, 2010, 2015, I would say that now we have a good recipe to identify them. Okay? And the recipe is just to do gradient descent and to make a good choice for the activation function. Okay, so this is the same here with 5, 10, and finally 20 linear regions. And you see again that we can obtain an approximation which becomes better and better as we add more and more hidden units in the hidden layer. Okay? Okay. Now let's make this neural network a bit more complicated just to see how we can obtain this generic one. So the first extension of the one input, one output neural network is to consider the case where we would like to predict not one, but 2, 3, or as many as we want output values. Okay? So in this case, we need to predict a vector, and a simple way to do that so here in this case, so we have the first output as before, but we could add another output, okay, which we compute in a way which is similar to the first output, but using a new set of coefficients and offset. Okay? And you can do that for as many outputs that you want. Okay? So here you see an example of a neural network with one hidden layer made of 4 elements, H1, H2, H3, and H2 and H3. And then we define 2 outputs, each of them being defined as a linear combinations, a weighted sum of the hidden units. Okay? And they differ from one to the other by just having different set of parameters associated to them. Okay? So the V, you will have a first set of V coefficients, so V0, V00, V01, V02, V03, that you associate to the output at position 0, and then similarly for the second output at position 1, you will associate a new set of parameters, V10, V11, V12, V13. Okay? So if we do that, then it means that with 2 output units, the network will be able to model 2 functions at once, okay? One corresponding to its first output and the other for its second output. But these 2 functions will be related to one another, even though they will be different, they will be related to one another because they are sharing the same hidden units. Okay? And since it's precisely the hidden units which defines where the joints are located, you will have an output or 2 outputs which look like this. So you have, for example, the first function and the second function, so they are different, but they have in common that they change direction at the same locations. And the reason for that is because they share the same input values, the same hidden layer. Okay? So the 4 joints of these functions are constrained to be at the same positions because they share the same input, but the slopes and the height of the functions will vary independently because the slopes and the heights will directly be dependent on the V coefficients that you associate to each output. Okay? Okay, so this one is easy. We can extend the neural network also to have multiple inputs instead of having just one input. So in this case, if you want to extend the neural network with multiple inputs, what will change is how each hidden unit is being computed. So now if we have, let's say, 1, 2 inputs, 3 again. So what will change is how this hidden unit is computed. So before, what we had was that hj was the activation function of w0x plus b, okay, in the case of a single input. Now if we have multiple inputs, we just consider all of them. So we have, let's say, x0, x1, okay, and we'll just add them all together, multiplied by some coefficient, plus some offset, which is specific to this unit. Okay? And we have the J. Okay, so this is trivial. Now, that means we'll have something like this. Now we'll have functions of multiple inputs. Okay. So if you look at the values, for example, that the first unit can take, it's the value given by this expression before the activation function. Okay, so you have to look at all combinations of x0 and x1. Okay, so you can look that by just considering a region of the 2D space. So for example, from -1 to 1 for the 2 inputs. And then for each combination of these 2 inputs, you just plot the value of W00 times x0 plus W01 times x1 plus B0. Okay? And that defines simply an hyperplane in this case. Okay? So it's just, again, a linear function. Now it's a plane because we have a 2-dimensional input. Okay, which is just also, it comes with a slope, which is given by the W coefficients, with an n offset. Okay, and again, depending on the values of the parameters, the W and the B, you may have a plane which is at some position, okay, at some orientation, and at some position vertically. Okay? So here you see 3 possible hyperplanes, one for the 3 hidden units. Then this hyperplane, again, they enter they enter an activation function, the ReLU, and the effect will be, again, similar as before. Everything which is positive will pass through the activation function. Everything which is negative will be set to 0. Okay? So when you take this hyperplane, you pass it through a ReLU. The result, for example, could be this one, where you see here everything to the right of the line corresponds to the positive part and is preserved, and everything to the left of the line before was corresponding to negative values, but now they become just 0. Okay? So again, that transforms your input into some kind of piecewise function where you have either 0 or the input itself. So this is for the first hidden unit. This would be for the second. Here you have the positive part. Here the values corresponding to the negative parts, which become 0. And finally here you have the positive part and the zeros there. Okay? Then now these values again are being mixed together through a weighted sum to compute the output. Okay? So you reweight each value h0, h1, h2 by some coefficients, like v0, v1, or v2. Again, the effect will be that you will change the slope of the positive part or flip it. Okay? So, for example, this one, certainly here the slope becomes, so v0 is negative, and everything which was positive before becomes negative, going to black. Okay? Here you see that the slope is steeper, okay, by just looking at the isocontours. So here the slope v1 is larger than 1 and positive, and here you have something which before it was positive, now it becomes darker, so it's the slope, the v0, v2 coefficient is negative, and you see that the isocontour now they are more distant, which means that the slope in this case, or the amplitude of the slope is smaller than 1. Okay? And finally, now you have these three hyperplanes. You sum them together, and you obtain the output, which you may also shift by some coefficient c. Okay? And now you see that we have again a piecewise linear function. Okay? But now the pieces, they are defined on the 2D space. Okay? You have this, they are no longer segments, they are some kind of shards of the input space. The number of input regions also will be dependent on the number of hidden units that you have in the hidden layer. And again, you can imagine that if you were to add more and more and more hidden units in your hidden layers, you would see more and more of these linear regions. Okay, so the story is really the same in 2D, and then you can imagine that it will remain the same in n-dimensional spaces for any n that you pick. Questions? Okay. All right. Now we are almost ready to obtain our first deep neural network. And the way I will arrive to that will be by just trying to consider what would happen if you take two of these shallow neural networks and you chain them together. Okay? So you have a first neural network taking x as input, passing through a hidden layer of 3 elements, producing some output y. Okay? And then you say this output y, you will pass it to another shallow network. Let's say of, again, one single layer of 3 elements. That will produce a new hidden layer, which I will call h prime. And then this vector h prime will be used to compute the output of the second neural network. Okay? So mathematically, this would correspond to this set of equations. Okay, we just do the same as before. The first 4 equations correspond to the first shallow networks, and the 4 last equations correspond to the second, where we use as input the output of the first neural network. Okay, now it becomes interesting. So what will happen is that this neural network, now made of 2 layers, will also define a piecewise linear function. Okay, exactly as before. I mean, similarly as before, not in the same way. And this is, for example, the output that you could have from this composition of two shallow networks. So you see that it's indeed piecewise linear, but now we have many more linear regions as we had, for example, by just looking at the output of the first neural network. Okay, so what's going on? So we could have, for example, so let's assume that the parameters are fixed. Okay, they produce. So that means when you pass some input values, x from -1 to 1, that will result in some function which we know to be piecewise linear, and the number of linear regions correspond to the number of plus 1 to the number of hidden units. So we could have, for example, for a tree, in the case of a neural network with only 3 elements in its hidden layer, okay, we could have this output, okay, where we have 4, 3 plus 1 linear regions. Oh, no. In this case, there are only, yeah, we only see 3 of them. So there are 3, in this case, 3 linear regions, okay? From -1 to 0, from 0 to this number, and from this to 1. Okay? Now, this will produce some output values y, which now will be used as input to the second neural network. And if this second neural network is also something very simple, 1 hidden layer, 3 hidden units, it will also define a function, a piecewise linear function, which could look like this function. Now, what is more interesting is what happens when you look at the composition of these two neural networks. So here, for example, when you go from -1 to 0, okay, in terms of the output, we are spanning the space from -1 to 1. Okay, so that means let me do that. So neural network 1. So let's take something similar. -1, 0, 1. -1, 1, 0. One. À peu près. Okay. Now, okay, let's consider this part for now. And what we'll be looking at is the composition x, so starting from x and producing y. Okay. Okay. So when we go from -1 to 1 in X space, okay, we are basically spanning, when we go this direction, we span this range of values in the output space of the first neural network. So that spans the range from -1 to 1. Okay? These values now will be used as input to this neural network. Okay? And then for each of them, I mean, and the result will correspond to this part of this kind of function that you see there. So that means from -1 to 0, okay, in this range, I mean, for the values x in this range, will span the same function, but compressed in a sense. And we'll have something like this. Okay, it's the same function but compressed. Okay. Now here, if we look at this one, let's call it 0,7, so that we agree on this. When we go from 0 to 0,7, so we go in this way, and we'll be spanning this part, this range of values for the output of the first neural network. So from 1 to -1. Okay, so it's as if we are taking this value and we place them here, but in the other direction. Okay, and so the output that we'll produce will be the same function, but compressed in this interval and flipped, because we are now scanning the range from 1 to -1 in the opposite direction. So it's the mirror of this. Something like this. And then finally, we are there. We have this part of the input from 0.7 to 1. Again, in this smaller interval will still span the interval from -1 to 1. So these values will produce all these values, which will be placed in this interval. Okay, and here we have okay, does that make sense? So that means effectively that each input region that the first neural network defines will be passed itself to another neural network, the second neural network, and the effect of this neural network will be to divide further within this region, the region, into smaller pieces. Okay? So this first region has been divided through the second neural network into this other regions. And similarly, this second region that we obtained from the first neural network is itself divided by the second neural network into subregions, and so on and so forth. Okay? Another way to view that is by viewing neural network as some kind of folding of the input space. So this would be, for example, what the first neural network defines. It defines this function, as we have said before, and it means that all these elements, so all these elements, and these elements, will produce the same output. Okay, so it's as if you had folded on top of one another all these input regions together. Okay, and indeed, all these regions together, now they produce the same output. And then you pass this folded sheet of paper, your folded input space, to another neural network, which will keep doing the same thing. It will also fold its own input space into other parts. And so you can repeat that with 1, 2, 3, or as many layers as you want. And the result is what happens when you look at, you take your input space and you unfold it. Okay, you will see many lines, and these lines correspond to all the input regions that you identify with the neural networks. Okay? All right. So this was the case of one-dimensional inputs. You can also look at what would happen if you start from a two-dimensional input shallow network. So 2 inputs, 3 hidden units, 1 output. And then you compose this neural network with another neural network made, let's say, of 1 hidden layer, 2 hidden units, and 1 output. Okay? So let's say this corresponds to the input y, as before. And let's say this function corresponds to the mapping from y to y prime, as defined by this very small but second neural network. Okay? What will happen is that now you will take every one of these linear regions, and you will pass them through independently through this function, and the result will be that could be, for example, this one, where what you see is that you have the same coarse linear regions as before, but each of them now has also been divided into 2 smaller subregions because they've passed through this activation, through this second neural network. Okay, for example, if you look at this part of the input space, you pass it through this function, and the result is this. But now we have 2 parts, 2 subregions, and these lines here that you see there is the result of this jump. Okay? Do you have questions about this? Okay. Shall I continue or shall we take a break? Okay, let's take a break and we'll resume in 10-15 minutes. Okay, we'll continue. Okay, so we were just there when we consider the composition of 2 shallow networks. So you could have, for example, this first shallow networks, 2 inputs, 3 values in its hidden layer, producing 1 output, and then you feed that single output to another neural network, which would map itself this value to some hidden layer, let's say 2 of them, and then this hidden layer would be used as input to produce the final output of the second network and of the composition of these 2 neural networks. Okay? All right, so if we do that, there is something that we should realize is that since the mapping from H to Y is linear, and since the mapping from Y to the input of the activation function is also linear, the composition of these 2 linear operations in series is also a linear operation. Okay? So this neural network is actually a special case of a more generic neural network where you would have an input as before mapped to a first hidden layer producing a first vector of values. And then if you and then what would happen is that this vector could also be used as input to a second hidden layer. Okay, so this one is actually a special case of this more generic neural network, where we have Y, where instead of going through this intermediate Y output, we directly use the output of the first layer as input to a second layer. Okay, where, for example, this element would be computed from this one, and this one. Okay, so in equations you could have something like this that you have in the slides. So we compute the first hidden layer by doing a linear operation plus an activation function like the redo. Then we use this vector, this three-dimensional vector now, as input to a second layer, which is defined as before as a layer taking as input some vector and producing as output another vector. Okay? So we could have something like this. Now we have it's as if the second layer was similar to this case, the multivariate input case, okay, where the input is not x, but the three-dimensional vector that we've produced through the first layer. Okay? And then finally, so then we compute the output of the second layer, and we use it to produce the final output of the neural network. Okay? Again, by just doing a weighted sum of the activation values, but now of the second layer instead of the first one. Okay? So the diagram now would correspond to something like this. So going from the input to the output, x, then the first hidden layer, then the second hidden layer, where you compute the second hidden layer using as input the output of the previous layer, and then you produce the output of the neural network using the output of the second layer instead of the first layer. All right, so again, we can decompose what is being computed. So here what you see, so this function could be the result of some linear combination of the outputs of the first layer, exactly as before. This is the same function as we had, but we call this expression y. Okay, but it's the same. But for some other values of the coefficients, well, this one, we could have another function, like this one, where again you see that the joints are at the same positions, but the function otherwise is different. And similarly, for the third plot here, which would correspond to another weighted combination of the inputs. And these weighted combinations of the outputs of the first layer are exactly what is entering the activation functions of the second layer. Okay? So if the activation functions are once again ReLU activation functions, you just keep everything which is positive and then truncate everything negative and set it to 0. And so this part here would become negative, would become 0, and this part here would also become 0. And we would go from this to that after passing through the ReLU activation function. And similarly for this input, producing this output, and this one. Again, so what you see here are the output of the second hidden layer, and then finally to produce the final output, we just do a weighted sum of these functions, okay, which again could flip or rescaled the functions. So here it's flipped, here it's rescaled up, and here it's rescaled down a bit. Then you sum all these three functions together, and that produces the final output, which is this function. Okay? So again, you see it's a piecewise linear function, except that now we have many more segments as we had before. Okay, so now we are ready to see the general formulation of this deep neural network. So the first thing is that the computation of a hidden layer can be written in matrix form. Okay, so if we realize that the output of a hidden layer is just a vector, and each element of this vector is a weighted sum of its inputs, so by using some coefficients that we call W. Okay, so to compute H0, you do the dot product of the first row of this matrix and of the elements of this vector. Okay? And then you add some offset B0. That's how you compute the first element of H. So we can do that for all q elements of the vector H, and in this case, we would have in this matrix as many rows as we have elements in the hidden layer. So we'd have q rows, and we would have as many columns as we have input values in X. Okay? So that means these can be compactly be rewritten as a matrix vector product where we do W transposed times X, a vector, plus B, a vector, where W transpose, or W, is a D times Q matrix. So D, the dimension of the input, and Q, the dimension of the output. So in this case, the dimension of the output layer, of the hidden layer. Okay? And B now is graded to a Q-dimensional vector. Okay? So a hidden layer is computed like this. And now if we say that we'll be composing several layers, okay, then it's as if we are saying that, okay, let's call H0 the input of the neural network itself. And then we'll pass this vector into a first hidden layer, okay, which will compute something like this. So you multiply the input H0 by some matrix W1, you add some offset B1, you pass everything to an activation function like a ReLU, and that produces a new vector H1 of dimension Q. And then you can say, okay, this vector of dimension Q, you will pass it through a node, a next layer, a next hidden layer, which will work in a similar way. So it will take its input H1 and will multiply it by some matrix, will add some offset, and then pass everything through an activation function to produce a next vector H2. And you can repeat that for as many layers as you want, let's say L of them. And finally, you say that the output of the last layer is the output of your neural network. Okay? So this architecture is what we call the multi-layer perceptron in deep learning, or the feed-forward neural network, or the fully connected neural network. These are all synonymous. I will call this neural network a multi-layer perceptron. Okay? Questions? Okay. So this is not too important for you, but you are also free when you design a neural network to pick other activation functions. So we have seen two of them so far. We have seen the sigmoid activation function, which appeared in the logistic regression model, and we have seen the ReLU activation function. These activation functions, they are really, really super important. If you remove them, nothing will work. Okay, and I will show you that in code. Which one you should use will depend on what you want to do. For now, you should just know that there are several of them. They exist. If you stick to a ReLU activation function, everything will work more or less. If you consider the sigmoid activation function, which is like this one that you see there for sig, it will work with maybe 2 or 3 layers, but if you add more and more layers, you will not be able to train these neural networks for reasons that I can explain in another course, but not today. Okay? So they are also important basically to make the optimization process easier. For some of them, and specifically those that saturate within some range, like the sigmoid, which saturates at 0 or at 1, well, then you may have troubles because the gradients that you need to do gradient descent basically will vanish to 0, and you will not be able to make any progress. Okay, next is how you design the output layer, so the output of your neural network. So we have something like this. We have some vector x. We said that we would have a bunch of layers. let's say L minus 1, and then we want to produce some final output Y, which is HL. Okay? How you should define this last computation will depend on the kind of problem you want to solve in the first place. If you say that you are interested in a regression problem, so when y should be, for example, some real value, then you could define y or HL as simply some vector W of coefficients that you multiply with HL minus 1 without doing the activation function. Okay? If you have a classification problem, then you can say that that y being equal to HL is, for example, the same as a logistic regression unit. So in this case, using a sigmoid activation function of some weighted sum of the elements from the previous layer. Okay, and then you can interpret this number, for example, as the probability value that you associate to, let's say, the positive class given X. Okay, and if you have a multi-class classification problem, so, for example, you have 3 classes, 10 classes, 100 classes, then you need to predict more than one number. Now you need to predict a vector of probability values, one for each of the possible outcomes. So let's say you have C possible outcomes, then you need to produce as output a whole vector of probability values. And if you want to interpret them as proper probability values, each of these values should be positive, and when you sum them all together, you should get the value of 1. Okay? And so you can do that by using a softmax activation function, which takes as input a vector, in this case the vector HL minus 1. And then what does it do? It just takes the exponential of each element, and this will ensure the positivity of each value. And then you normalize by just dividing by the sum of the exponentiated values that you have obtained before. Okay? And the result now is a vector of numbers that you can interpret as a vector of probability estimates. Next, how do you tune the parameters of these neural networks? And in this case, the parameters are all the W matrices, all the B vectors. Okay? And you may have many, many of them now, or these matrices can be quite large. But the recipe is still the same. So the objective function are something that you can derive directly from the likelihood. Okay, so as before, if you have, for example, a regression problem, you can say that Py given X follows a Gaussian distribution. Okay, but now the mean of this Gaussian distribution would not just be Wt times X plus B, but would be the output, for example, of your neural network. Okay, and then again, that would simplify to just minimizing, for example, the sum of squared error between the values that you have in your data and the values that you predict as output of the neural network. Okay, and for classification, if you assume now not a Gaussian likelihood because it would not make any sense for classification problem, but a categorical likelihood, then we have the same setting as before for the logistic regression unit, and you would obtain as a loss the cross entropy, which in the case of multi-class classification, so you have C classes, would reduce to this expression. Questions? No? Okay, so let's switch to an example then. Okay. So this is the same example as last week, where we're trying to solve this classification problem. We have two-dimensional inputs, the coordinate of a point on the 2D plane, and we want to say if this point should be from one or the other class. Is it yellow or is it black or dark or something? Okay? And we saw that we could try to solve this problem using a linear model. So in this case, the logistic regression model, which I can define simply as a linear projection of the data, which would do W transpose times X, and then you pass this value to a sigmoid activation function. And then you interpret the value again as the value of the positive class. Then you have a training loop, where at every step, so every iteration would correspond to an iteration of gradient descent. And what do we do at each iteration? We evaluate the loss function. So in this case, the loss function criterion would be BCE loss, the binary cross-entropy loss, which is the one we've derived. And then you can forget about all these lines. They are not important. What is important is this. So in these two lines, you would compute the gradients of your loss with respect to the parameters of your model, and then you would make a step of gradient descent. And then you iterate like this, in this case for 2,000 iterations. And if you do that, you would arrive to this kind of model after fitting, after training, in which most of the yellow dots are put all together, and most of the dots from the other class are also put together. But of course, since obviously you cannot linearly separate these points, there is only so much you can do with the linear model, and all these points in this region or in this region will be incorrectly classified. Okay? All right. So now we'll see what happens when we use instead an MLP, a multi-layer perceptron, exactly like the ones we've covered this morning. So the first thing is that I will just start from the same model as before, the same linear model as before. So let me just do this. Linear DC. Okay, so this is the same linear layer, and I'm just replacing the sigmoid by a softmax, but when I have two classes, it's just the same. The loss is the negative log likelihood, which we know will correspond exactly to the same as the cross entropy, and other than that, all the other lines of codes are the same as before. Okay, so if I run this, okay, I get the similar results because my model remains a linear model. Okay, now something that I've already mentioned, if you compose in series two linear operations, you still obtain a linear, it's as if we had done only one linear operation. Okay, so if I say that I'm so I go from a d-dimensional vector through a linear projection to a new vector of dimension h, and then I again project this vector of dimension h now to a vector of dimension c. Okay, since these two operations are linear, their composition is linear, and we should not get results that are any different from before. Except that now we have more parameters because we parameterize the projection in terms of two matrices. Okay, the projection is defined by the product of these two matrices instead of one matrix only. And where we'll end up may be different because of gradient descent. Okay, which is random. Okay, and we have no guarantee that we'll find the global meaning. That will depend on where we start in the parameter space. Okay, and now what I will do is that I will consider a shallow neural network, okay, where I first project my input of dimension d to a hidden layer. And I do that by doing a linear projection, then a ReLU. Okay, it's exactly like this. And then this linear, and then this vector of hidden values, I project them to compute the output. Okay, and I do that by doing a linear projection and then a softmax. Okay, and you see that the code remains the same. Now, what will happen if I do that? Okay, so now you see that we managed to fit the data. We can separate the yellow points from the other points. Okay, and the reason is because we've introduced these nonlinear activation functions. That's the only change we've done. I've just inserted this ReLU, okay, which may look like just one, and this is really one line of code, but the results are quite different. Okay. So here I'm projecting the data into a vector of size 100. Okay, I'm also free to decide on the value. Let's say I project this data only to 10 elements. What do you think will happen? What's your intuition? So from what I've explained this morning, the size of the hidden layer will basically define how many regions how many linear regions we define in the input space. So if I reduce it, I should have fewer of these regions. And what you should expect is that the boundary decision here, you will see certainly more segments as before, more linear segments as we had before. So let's see, 10. Okay, this one didn't work as well because we have too few, maybe too few. Okay, but clearly, so it does not work as well, but clearly you see that we have these linear regions, these linear segments. You see them appearing clearly in the decision boundary. If I increase, or let's say I decrease it even further to 5, okay, you see that we have, it works slightly better, but we should have fewer of them. And if I increase that, let's say to 50, it's still piecewise linear, but since we have so many of them now, it looks as if it was a smooth curve, but it's not. If we were zooming in on one of these regions, we would see also these linear segments. What do you think will happen if I increase that to 1,000? Yeah. Too many what? Yeah, too many expanding nodes, maybe. Yeah. Sure. Okay, let's see. Okay, so it works as well as before, except that now we have the curve is maybe not as smooth as before. We have this kind of artifacts, okay, which we may wonder if they are really meaningful, but this is what has been discovered by training. What do you think will happen if I keep increasing that to 10,000 or 100,000?
Some sort of overfitting?
What is overfitting?
Maybe some spikes.
Some spikes? What do you mean?
Or it will be less smooth.
Less smooth. Okay, so let's see. Oh, fuck. Okay, I will try again. Tac. Okay. So we tried with 1,000. Let's say 10,000. Okay. So it's slower. You see that it's updated less frequently. It's because now we have more parameters. Yeah, by the way, how many parameters do we have? Can you estimate how many of them we have if we have 10,000 elements in the hidden layer? 10,000 minus 1. Any other guess? Okay, so how many parameters do we have? We need a matrix here, and the offsets. Okay? This matrix is of size, so number of inputs, 2, times number of outputs, which in this case is the size of the hidden layer, so 10,000. Then we have a vector of B, which is the same size as the hidden layer, so plus 10,000. And then we produce one output, the probability values for the positive class. And so here we are mapping a vector of size 10,000 to one element. Actually, in the softmax, you would be mapping that to 2 elements. So we have 10,000 inputs times 2 outputs, plus, again, a B vector. And in this case, we would have 2 B vectors, one for each of the 2 outputs. OK, and if you sum, we have 2, 3, 4, 5, 70,000 parameters, more or less. OK? Do you see it spiking? Why? So one thing also you should realize is that I have many, many more parameters that I have training points. Okay, the number of points that you see there is maybe in the hundreds. I don't know how many I've used actually. 400 of them. And I'm using 70,000 parameters to fit this data set. So in this case, we are not overfitting. We could have overfit the data, but we are not. And actually, if I add more memory in my computer, I could increase that to several millions, and you would not see any sign of overfitting. Okay? Actually, you would get a curve which becomes smoother and smoother. Okay. Okay, let's go back to 100. Or maybe 10. So with 10, this is what we add. So clearly, in this case, the capacity of the network is not large enough. And I could increase the capacity by either adding more nodes in this hidden layer, or what we've also seen is that I could add maybe other layers. I could add a second hidden layer, and maybe I could add just suggesting wrong things. Well. Okay, so I can add another layer of size h, okay, and then the second layer will be mapped finally to the output of size c. And this second layer has also a size of 10, okay, as the first one. So do you think we'll do as well as just having one layer of 20 units if we have instead 2 layers of 10 units each? Let's see. Okay, we get something like this. And we could repeat that if you want. So this is with 10 plus 10. If we had used, I don't know, 20, this is what, and only one layer then. And you, boom. Which is slightly worse in this case. But so what will happen is that you will gain capacity either way by increasing the width of a layer or adding more layers, but you will gain more capacity by adding more layers. Okay, because that gives you the opportunity to divide each linear region into subregions instead of just adding more regions. So in this case, the increase of capacity, in a sense, is exponential in the number of layers, and it's linear in the width of a layer. What else can I show you? Yeah, the effect of the activation function, maybe. Okay, 10, 10. Okay, so this is the two-layer MLP with 10 hidden units in each. This is what we add. Okay, you see that sometimes it does not work. So here you see clearly the linear segments. They are a result of the ReLU activation functions. We have seen others. So we have seen, for example, the sigmoid activation function. So I could replace this. So now we see it's smooth, but it doesn't work very well. There are others that we have seen. Let's go back here. I don't know. Could use this one, for example, cell U. Yeah. Okay, it's a bit better, but not maybe the most appropriate for this problem, or maybe if we had trained for longer, it would be better. But now you see that you don't see the same linear divisions because now we are using a function. I mean, you still see some crisp division. This is because we have a discontinuity there in the CELU activation function. If we had used, I don't know, this one, LU. Yeah, this one does not work very well. If I increase that, I don't know, 50. Okay. So which one you should pick and when you should pick one over the other is quite an art, I would say. There is no good guidelines so far. But if for now you start playing with neural network, use ReLU activation functions, they will work most of the time and it will make the optimization quite easy. They may not give you the best results, okay, but they will give you good results nonetheless. Okay, and then finally, we can also see what would happen if we had a multi-class classification problem. So let's say we have 4 classes, and now we would have this kind of data, like this. So we have 4 arms in the spiral, and each one defines a category. So yellow, dark blue, and green. And again, we want to try to classify these points. So we could do that. We could try to do that with a linear model, but now we would have one linear model per possible outcome, and then we would feed that through a softmax activation function. So it's as if we had one hidden layer shallow network, but without the hidden layer. So we directly go from inputs to outputs, okay, and that's it. Okay, good enough. We have these 4 parts because we have 4 regions. Certainly, if you had trained longer, it would be slightly better. But again, there is only so much we could do to separate these data points with 4 lines. If we have an MLP instead, and I will go back to ReLU, 2 layers, 50 nodes per layer. Okay, same story, except that now we are just predicting 4 outputs at once, one for each of the 4 outcomes. Okay? Questions? Okay. Okay, now, so this is more or less what you should know at this stage in this course about neural networks. What I will do now is to give you a short introduction about more interesting architectures, even though this one is actually quite powerful already. It's universally powerful. You can approximate any function already with these MLPs. But what you may notice is that they may not be appropriate for all cases. And one first instance of this issue is, what do you think would happen if you were trying to train one of these MLP on images? Okay, if we go back to our initial problem, you would have images of cats and dogs, and you want to predict a binary outcome, cat or dog. What do you think would happen if you feed the image as input and then through a bunch of layers to produce the output? Yeah.
So when the inputs, maybe that you need a lot of hidden nodes to have any meaningful outputs.
Yeah, so a first issue is the number of parameters. So if you have here, if you have an image of size h times w and usually times 3, because you have 3 channels for the pixels, red, green, and blue. So you would have each pixels defined by 3 numbers, and you would have as inputs, if you put everything into a very long vector, h times w times 3 input elements in x. Okay? So let's say that you feed that to a hidden layer of size, I don't know, 10, 100. I don't know, let's say 100 for Q. Then already in the matrix W0 would be a matrix of size, number of inputs, and number of outputs. So in this case would be h times w times 3 times q, 100. Okay? So if you have images, I don't know, low resolution images like, I don't know, 200 pixels by 200 pixels, okay, which are quite small, you would have 200 by 200. So that's 40,000 times 3 times 100. So already the first, just for the first matrix, the very first layer, you would have 12 million parameters. And in the case of images, having only 100, a size of 100 for the first layer is maybe not enough. Certainly, you would need many more hidden units. So this would not scale already because of the size of the parameters or the matrices that you need when you do these linear projections. So that's the first problem. Can you see another problem? Let's say you're given the image of a dog, and I ask you, is it a dog or not? Do you need to look at the entire image to make this decision? If it's a big image where there is a dog somewhere, do you need to look at the entire image? No. Okay? So, but when you architecture an MLP, these hidden units will be connected, or all the pixel radars will be connected to these hidden units. So what is being computed by this unit is a function of the entire image. Okay? Maybe you could have a computation which is only local to maybe this part of the image. Okay? And if we make this local, that means it will also reduce the size of the matrix, because now it will become a band matrix. Okay? So intuitively, this is what you can architecture in a CNN. Okay, so the lesson is that the multi-layer perceptron architecture will work well for tabular data when you have input features. That makes sense already on their own, but that will not work for images. Okay? And one first reason is that in that case, each pixels of the image would be an input feature, so one element in this X vector leading to a very high dimensional input vector, and then also leading to a gigantic matrix in the first layer. Okay? And second, each hidden unit would also be connected to all inputs, and the two of them together would lead to this high dimensional weight matrix. What we could do instead is to try to have a neural network such that in the very first layers of this neural network, the network would respond similarly to similar patches of the image, regardless of their location. Okay, so if you have an image like this, I don't know, with a cat somewhere, okay, you could have the network to look at this image by patches, okay, and how the neural network would respond would be the same regardless of the location of the passage. Okay, so that means you would apply the same function on the patches regardless of where is the patch. Okay, so you would look, basically what I'm saying is that it could be interesting to architecture this first layer such that the computation that you would do would only look at small regions in isolations of the others. Okay? Because in that case, you would basically just apply a neural network on a very small part of the image, and then you would apply this everywhere, that same function everywhere on the entire image. And the reason you could do that is that if you were to do that, the earliest layer could focus on local regions of the image. Without considering the contents of distant regions in that image. Okay? And then what we could also try to do is that in the later layers of the neural network, we could try to recombine information we have collected in one part of the image with information that we've collected in another part of the image to then produce a new information, a new representation of the data, and go on until we reach the output of the network. So intuitively, these ideas can be framed into what we call a convolutional neural network, or CNN or ConvNet. It will basically extend what we have seen, the multi-layer perceptron, with two new kinds of layers. The first one is what we call a convolutional layer, which will be acting as a local feature detector. And the second one is what you call a pooling layer, which will basically reduce the spatial dimension of your signal. Okay, in the case of the image, this pooling layer would be the same as just reducing the size of, rescaling, resizing the images by some constant factor. Okay, and you have one such convolutional neural network below, where you have a first convolutional layer, which would produce a new representation of the input using an operation which we call a convolution, which you will see will be very similar to just a dot product. Then we pass this information to a nonlinear activation function like a ReLU. And then, so this is the same as what we had before. We have something which will be close to a linear operation, which will be a linear operation, and then we pass it through an activation function. Okay, that gives you these images, and then we will be rescaling using these pooling layers. Okay, and again, we'll then add more convolutions, ReLUs, and so on and so forth. So this is for the high-level overview. These convolutions, they are defined in this way. So I will define it first for the one-dimensional case, where we have just vectors. And then I will generalize that for images in 3D. OK, so let's assume that we have a one-dimensional input, x, of size w. Okay. Then I will define a convolutional kernel u as a smaller vector of size lowercase w. And I will define the discrete convolution, which I will denote as x star u, as a vector of size w minus w, so the size of the input minus the size of the kernel, plus 1. And I will say that each element of these vectors of this size will be computed in this way by just computing the sum of the product of the input values and the kernel values, okay, within some window of the input, and the window will be defined by the kernel. Okay, so let's take an example. Let's say we have as input this vector 0, 0, 0, 1, 2, 3, 4, 4, 4. And we convolve it with this kernel defined by these two elements, minus 1, 1. Okay? The way you would compute that so 0, 0, 0, 0, 1, 2, 3, 4. This is x. And now I will be computing x convolved with u. And the way you do that is that you just consider every possible locations of the kernel inside the input. So you could place minus 1, 1 here at this position, or there, or there, or there. Okay? And for every possible location, you just multiply these elements together and you sum. Okay, so you do 0 times minus 1 plus 0 times 1. That gives you 0. Okay, this is x star u at position 0. Okay? Then you would have the other next position, minus 1, 1, that gives you 0. Then the next one here, that gives you 0. Then this one is interesting because we would have 0 times minus 1, 0, plus 1 times 1, 1. Then the next position, we have this one. So here we would have 1 times minus 1 plus 2 times 1, 2, so that's minus 1 plus minus 1 plus 2, 1. Okay? And then you can repeat that to obtain the rest of the computation. Okay? And so how should you interpret that? Basically, what will happen is that you have this kernel, which you can view, really consider or interpret as a local feature detector. You are trying to see if some features that you define through the values that you put in this vector do match with some region in the input. So you are basically computing, does this match with this region in the input? Does this match with this region? Does this match with this region? And so on and so forth. And we are doing this matching using a similarity measure. And the similarity measure that you're basically using is the dot product. Okay, you can always interpret a dot product as a similarity between two vectors, and that's effectively what you are doing. And that's why, actually, we are using this very expression. This is just a dot product between the kernel and a subregion of the input. Okay? And then this vector that you get is just the vector of all the similarity measures between the kernel and the input. Okay? You have another example here with a three-dimensional kernel. You repeat the same thing, and basically here what you will see is, so here what you would obtain, you would identify regions in which there is a change in values, in which the function basically is increasing, and indeed, after the convolution, you have a match with these four values, which correspond to when the function increases. And here, what you would have a match when you have two values and nothing in between. So when you basically look at how similar is each region of the input with respect to this kernel, then you would have a high match here, and you would have half a match for this, and you would have 0 everywhere else. Okay, and that's exactly what you get. You have it's half matching when you have only one bump. When you have the two of them at the right place, it's matching even more. Otherwise, it's 0. Okay? Then you can extend that to images. So this was for the one-dimensional case, but you could say that you have an input which is a 3D tensor. So of size C, number of channels, typically 3 RGB, times H times W. And then you would have, similarly, kernels. So in this case, you would have a kernel which is also a tensor of size C times H times W. Okay, and you would apply a similar formula, but it's the same as before in the one-dimensional case. Okay, and so visually, what would happen is that you would, if this is your image, then you would, and this is your kernel, you would just consider every possible locations of the kernel within the volume of the image. And then for each possible location where it can fit, you compute this sum of products between the pixel values and the kernel coefficients. You sum everything, and you report this number at the corresponding location in the output. That's it. That's all it's doing. And you could have one or several kernels if you want. Okay, in this case, if you have two kernels, then you would just be computing a second output, in this case, a second slice in your output volume. Okay, now that we have this, you should see that there is a parallel between a convolution and a regular linear layer. So what we have seen this morning is this case where you connect all the inputs, or rather, if you are computing some hidden layer, you do it by using all the outputs from the previous layer. Okay, so that means each hidden node in the hidden layer is connected to all inputs to all elements in the previous layer. Okay, and effectively that would result in a matrix like this, a W which is dense. Okay, where you have numbers everywhere. In a convolution, you have something similar but different in two interesting ways. The first is that a convolution, because it applies the dot product only locally, it will each element here, let's say H2, will not be computed using all the previous elements. It will only look at a subset of this element. Okay? So, for example, H2 would be computed from X1, X2, and X3, but not X4, not X5, and not X6. And similarly, H5 would be computed for X4, X5, and X6, but not the others. Okay? So that means effectively, in the corresponding weight matrix, many of the entries will be set to zeros because we don't have these connections. And what is even more important is that, so that's first, that's how we get the locality. And second, these weights that you use now in a convolutional layer, they are no longer specific to each unit, they are shared. So that means the coefficients that you would use here to compute H3, so the black value, the orange, and the brown ones, will be exactly the same as the coefficients that you use for the other values, let's say H4. Okay, so you share the parameters. Okay, so effectively here, the number of parameters, okay, it's not 6 by 6 as in a fully connected layer, it's only 3. Okay, so we've reduced by quite a lot the number of parameters. And the reason we are sharing the parameters is because we are saying that what we are computing is not, should not be important. The location of what we are computing should not matter. Okay, so that's why we are just replicating the same computation everywhere, and we do this replication by just sharing the weights, sharing the parameters. Okay? Okay, pooling. So pooling is easy. You just take a vector or a 3D volume, and then you resize it, okay, by, let's say, a factor of 2. And the way you would do that would be, for example, by dividing the input into smaller parts, and then compute an output, which will be smaller by a factor which you have to define, let's say by a factor of 2 by 2. And in each element of this input, you just compute, for example, the maximum value of the elements in the corresponding region in the input, or the average value in these regions. Okay, so you divide basically your input into tiles, and then for each of the tiles, you compute a small function to aggregate all these values together. Like you take the maximum value, or you take the mean value, and you report it in the output. And so this would be what would happen. Let's say you consider pooling regions, pooling areas as the one you see in gray. And then you just consider every possible locations of these and disjoint locations of these pooling areas. You compute this max, and you report the max in the output. And effectively, what you would obtain as output is now a coarser version of this input at a lower resolution. Okay, there is a notebook, if you want, on the GitHub, where you can see a sketch of a CNN. And in the notebook, you will see a comparison between an MLP and a CNN. And you'll see that, indeed, we gain by using an architecture like this one, or at least on images. Okay, so I see that I have 15 minutes left. So what you should understand from the CNNs is that they are very similar to the MLPs. Okay, you can view the convolution as a linear operation, but with two properties. It's local, so that means the weight matrix is sparse, and you share the parameters. So you will replicate the parameters everywhere on this band. Okay. Recurrent neural network you can skip. But these are quite interesting if you want to process sequences. what I want to spend the last minutes on is the transformer architecture very quickly. So the transformer architecture is basically what is at the core of large language models, like models that you have, for example, in ChatGPT and in other chatbots. So how does it work? It works at its core with a neural network. And the goal of this neural network is just to produce sentences. It's to generate data. And the way it's doing that is by decomposing a sentence into tokens. For example, you can decompose a sentence at the word level, and you say that each token is a word, but you could divide the sentence at a smaller scale by saying that each sentence is a set of tokens where each token corresponds, let's say, to a pair of letters or characters. It's up to you. Okay, so you start from some input sentence, you tokenize it. That gives you, let's say, 5 parts. And then you transform this token, or you associate to this token, to vectors. Okay? So you could say that the word "the" is associated to a vector, let's say of 5 elements. The word "fish" is associated to another vector with the same dimension, and so on and so forth. And this set of vectors are passed to a large language model, so in this case, a neural network. And the goal of this neural network will be to make a guess about what is the next word, or what is the likely next word in that sentence. So how should you continue this sentence? The fish lived in the... Where do they live, the fish? In the ocean, okay? So, or in the sea, or whatever, okay? But in water. And so you have possible next words, and you have to determine which one is a good candidate. Okay? Does that remind you of a task that you have seen before? It's a classification task. Why is it a classification task?
Because every possible output is a different class, there's probability to choose each one.
Exactly. So you should. It's really a classification problem. Given the start of a sentence, or given this set of tokens or this set of vectors, what we want to do is to predict a possible next word, okay? Which is nothing else than a choice among all possible next words. Okay, so you have a dictionary for all possible words. What you have to predict is one of them. Okay, so you have C possible outcomes, and you have to pick. You have to make a guess about which one is the most likely. Okay, so that's a classification problem. And so effectively, these large language models will be trained as classifiers, okay, over many, many possible next words. Okay, but this is just a classification task. Okay, so this means if it's just a classification task, you train a large language model by minimizing a cross-entropy loss, exactly as what we have seen previously. Okay. Once you can solve this classification problem, then you can generate sentences. Okay? If this model gives you a probability vectors over all possible next words, then one way to generate sentences as random is just to then draw randomly, but proportionally to the probability that you compute, next words. Okay? So for example, if this is the top 7 of the most likely next words, then you would pick randomly but proportionally to their probabilities one of these words. Okay, so you draw a random number and then pick one of them. And so it could be, for example, that then the value that you select randomly is blue. Okay, and blue would be a new token which you add to the sentence. So that gives you a new element in the set, to which you also have a vector. And again, now you have the same problem as before. You have a set of vectors input, and you want to predict a class as output. Okay? And by doing so, then you would predict the next word of the sentence. And you could continue like this as long as you want. Okay? And so this is effectively how systems like ChatGPT works. They work exactly in this way, by just maintaining a set of tokens in a prompt, that's the sentence, and then continuing the sentence by just drawing these numbers, by just solving these classification problems at every step. Okay, so what we say is that for language modeling, the transformer, they will define what we call an autoregressive model that will predict the next word in a sequence given the previous words. So effectively, the probabilistic model that you have in this large language model is a probability distribution over sentences of T words, and you factorize it in an autoregressive way. So basically just using the product rule, as we have seen, and you say that this probability of a sentence is the probability of the first word times the product of the transitions, so of the next word given the previous ones. Okay? And if you want to go inside this kind of neural networks, so I've told you that these words, they are mapped to vectors through embeddings, but they are basically just a hash table, basically, or a dictionary. To each word, you associate a vector, and you say that the content of this dictionary now corresponds to parameters that you would have to learn. So you have already as many of these word embeddings as you have in your vocabulary. Okay, so that can be quite big if you have a large vocabulary, but fine. And then how do you produce the classification? It goes through a transformer architecture, which is something I will not detail in this course, but it's going through this part, which we call a self-attention layer, which is another variation of a linear layer, in a sense. Then these blue things are normalization layers, and these ones that you see there are small multi-layer perceptrons, exactly the ones that you have seen, that you apply independently to each token. Okay, so you apply a small MLP to this word, to this word, to this word, or at least to some new representation of these words, and you do that independently for each of them. You do that a bunch of times, so you have a large compositions of these transformer blocks. And then at the very end, when you have to design the output layer, what do you have? You have a linear projection followed by softmax that gives you a very large vector of probability estimates, where this vector is as large as the size of your vocabulary, and and for each entry you associate a probability value. Okay? And that's it. That's how it works. There is no more than that behind ChatGPT and other systems. What is interesting, what is surprising about these transformer architectures is how they scale. So what we have noticed in the research community is that this architecture is very, very good at just ingesting as much data as you want. So what we see is that as you increase the size of the data set in terms of tokens, in terms of words basically that you use to train this model, the performance or the error of this neural network will keep decreasing, and we don't see any sign of saturation. On the other hand, if you just train an MLP and keep increasing the size of your data set, eventually it will saturate. Usually it will saturate quite quickly. But for transformers, it's less the case. We also see that as you keep increasing the capacity in terms of number of parameters, you get better and better and better results. At some point with an MLP, if you keep increasing the width or the number of layers, you will also saturate. You will not see any improvement. But for transformers, again, we keep seeing improvements as we add more and more parameters. And finally, it's also the case in terms of compute. The longer you train this neural network, the better. But here again, if you train, or the neural network that I've used, if you train it for 10 seconds, it will be good. If you train the same neural networks for 2 hours, it will not be better. Okay, but that's not the case for the transformers. Questions? Okay. If not, then I will finish with a few real-world illustrations of all of this. So we'll not watch all these videos. I will just pick one of them. But this is just to tell you that everything we have seen is already being used in many, many applications. So every time you hear about AI, it's certainly a neural network below of different kinds. So for example, this is a video from NVIDIA where you have a few applications of neural networks. For example, to estimate, to classify pixels in an image, for example, in a car that would be driving itself, or to detect obstacles. You could have a system that detects the roads, detects pedestrians, detects road signs, and so on and so forth. You can do so by using a neural network. You can also detect individual objects and so on. In Tesla cars, in the autopilot system, you have also a bunch of neural networks. So of course everything is private, but they've disclosed a few years ago that they were using a big compositions that they call the HydraNet, which is a composition of more than 70 neural networks of different kinds, solving different tasks, but all trained together using the output of one as the input of the other and so on, to go from a feed of several cameras that are on board of the car, and then to transform everything into some kind of understanding of the surrounding of the car by going through some intermediate steps, like, again, segmenting the image, estimating the depth, but also from this to reconstruct a 3D scene of the environment, where you have the car, where you have the other cars that are moving and so on. And from that, you can continue and go and reach the final decision, which is what you should do with the car to go forward, to brake, to steer, and so on and so on. Okay? The last example, and this is the one we'll end with today, is how machine learning can be useful in medicine. So I think this one are very nice applications of AI. It's a bit old. It's already from 6 years ago, but it's closer to what we have seen today. So many neural networks that we have seen today, including like convolutional neural networks, can be directly useful for many interesting applications. And so we just watch this one.
There's been many innovations over the years that drive science. If you go back in history, many scientific insights actually derived from new tools that were able to measure new things. AI is very, very good at finding new paths that haven't been seen before. It's almost an enhancement on our ability to sense the world.
The main benefit of machine learning is the ability to learn from lots and lots of data.
We can show a computer a lot of examples, and rather than tell the model how to evaluate that data, it can learn actually how to interpret it and figure out what to do next.
Here at Google, we've been using machine learning technologies in all of our products. Things like search, translate, Google Photos, and the Assistant.
People are realizing that learning from examples is a very powerful tool.
So researchers in the healthcare community were looking at some of the work that Google was doing in artificial intelligence and actually reached out to us and said, is there a way that you could apply these same kind of technologies in healthcare? Doctors today have more artificial intelligence working for them on their smartphone for their personal use than they have working for them in a clinical context.
And as doctors, we've just gotten more information kind of shoved at us in terms of records, in terms of images.
Think about all the different types of cells that you have.
15,000 or 20,000 different diagnosis codes.
Just a cubic millimeter of tissue, it's like taking, a billion photos.
If you print it out, it would probably be about as tall as a 10-story building. Really, any kind of data that people can generate on a massive scale is really an area where machine learning can help.
Now there's an opportunity to use all our digital technologies that have been developed at Google to really try to help doctors.
Let's take some of these tools that are great for analyzing videos on YouTube and apply them to problems that matter to science.
One of the things we've been working on in medical imaging is in the area of pathology. Traditionally, pathologists take some tissue sample and they look around in the sea of cells looking for the needle in a haystack cancerous tissue.
We know that the earlier you detect the cancer, the greater your chance of curing it, and the greater your chance of curing it without chemotherapy or radiation. So the biggest challenges are speed and accuracy of diagnosis. So far, we've trained models for breast cancer, prostate cancer.
These technologies can actually identify suspicious areas to direct the doctor's attention.
So one of the things we wanted to do was get this work into the hands of as many people as possible.
And so we developed something called the augmented reality microscope, where you can actually see machine learning assistants overlaid in real time as you're looking through the microscope.
These units can be attached onto any existing microscope, greatly reducing the cost. We're really excited to bring machine learning to parts of the world with limited access. One of the tools some biologists use is they will dye cells with different colors to highlight certain important features that make sense to them.
The problem is we have to kill the cells in order to color them.
So we said, well, if we can do this virtually in a computer, we can preserve the cell in its natural state.
One of the things that you can do with a Pixel phone right now is given a selfie, you can predict the depth, and you can do interesting visual effects. So we thought, hey, can we take this same technology and apply it in a biological context? And essentially use machine learning to predict the stain. We weren't sure it would work or not, and it ended up working so well. We're very hopeful that this technology can be used to just have the computer generate pretty pictures that people know how to interpret.
The brain is probably the most complex physical object in the known universe. We know that there are these basic units called neurons, and they're connected in many different ways. What's shocking is how little is known about what those patterns of connectivity look like and what that means for how the brain works. The problem is very hard because the connections are too large to analyze. For example, fly brain has 100,000 neurons, whereas human brain has 100 billion neurons. So fortunately at Google, there's been already a lot of work put into dealing with data sets of that size. Machine learning and the computer vision technology that we've developed has been designed to accurately trace the wiring of the brain in 3D. Prior to that technology, it would have taken thousands of years to basically finish mapping the fly brain. Now you can do it within a year or two. It's a warm-up to understanding larger and more complex brains, hopefully human brains. We're hoping that mapping a brain could potentially help us understand a lot of the neurodegenerative disorders, for example, schizophrenia or Parkinson's, then we're going to be able to design better therapies that might improve those conditions.
There are tremendous inequities in the way that healthcare is distributed across the globe. Any disease or outcome is predicted as much by your zip code as it is by your biology.
So what can we do with AI to bring the expertise to where no expertise exists?
One of the complications of diabetes is diabetic retinopathy. It causes blindness, and it's diagnosed by seeing little lesions in the eye. But in India, there is a shortage of eye doctors, and as a result, about half the patients suffer some form of vision loss. This disease is completely preventable. This shouldn't really be happening. So we were able to train a model to read these images and match board-certified ophthalmologists. We're now figuring out how to deploy this into the clinic. In India, people who did not have access now have access.
A lot of science is driven by a hypothesis that someone has, but some of the biggest breakthroughs in science come from surprises, things no one expected to have happened.
One of the really exciting things about deep learning is where you can just give it the raw data and it finds the important features. That's interacting with scientists at a very different level and saying, well, let me show you something you've never seen before.
We had one research project where we were looking at human retinas, but what surprised us was machine learning started seeing things that people didn't know was possible.
Turns out that a deep learning model is actually able to identify things that have nothing to do with your eyes, like your cardiovascular health and your metabolic profile. These are things that if you had asked experts, what do you think we'll find, they would have said nothing.
The important thing about this is it's a visual biomarker that we did not know existed before.
Those unexpected things may lead to a whole new idea, a whole new approach, a whole new hypothesis for how to attack the problem you're trying to address.
There are real patients suffering today, and if we're not doing everything we can with all the technology at our disposal to help those patients, then what are we doing?
I think that 10 or 15 years from now, the use of machine learning in healthcare is just going to be how healthcare is done.
I think this is how we're going to find new discoveries. I think this is how we're going to find ways to take care of poor people.
The more we can accelerate that basic work and give all these scientists new tools, we will, as humans, really benefit from the new discoveries that one day end up in our doctor's offices.
Comments? Okay, you should realize that you can do all of this already with what you have seen in the last 2 months. No, but I'm not kidding. It's no more than convolutional neural networks. Okay. Okay. So you should, so deep learning is powerful, blah, 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 blah. So that's the main message, neural networks, neural networks. Basically, everything AI is neural networks these days. But really the key message is, at least from a more mathematical point of view, is that these neural networks, they are just compositions of simple blocks, simple bricks. We started from just a linear projection, passing through a nonlinear activation function. And when you start composing these very simple functions in parallel to obtain layers or in series to obtain a multi-layer perceptrons, then you get something which is very powerful and as powerful as you want. Okay, so mathematically you can prove that you can approximate almost any function. Okay, of course, to be efficient, then you need to introduce what we call inductive biases. You need to insert assumptions about what you know about the problem. Like in the case of images, you need convolutions to exploit locality, to also exploit scaling effects and all these things. This also can be put explicitly in the architectures, and then you can start composing these bricks on top of one another. And it's really the philosophy of deep learning. In my opinion, this is what you should remember mostly about these 2 lectures. All right, so we'll have an exercise session. Let's take a break of, let's say, 10 minutes, or let's resume at 11:20 with the exercise session. Thank you.